In this video, we will derive the equations of motion for a circular disk that rolls without slipping. A disk of radius r rolls on a flat surface without slipping. Let O be the center of the disk and point C be the location that is touching the ground. We will now derive equations that describe the motion of the center of the disk. After some time has passed, the disk has rotated an angle theta. The center of the disk has moved to O' and point C has moved to C'. If we could follow point C for a long enough period of time, we would see that it would trace out a V in space. Let's call the point that is now touching the ground point A. The distance between points O and O' is the same distance between point C and A. We'll call this distance SO. SO is also equal to the arc length from A to C', which is equal to theta times r. The instantaneous velocity of the center of the disk, VO, is the time rate of change of the displacement, SO. Plugging in theta times r for SO and pulling r out of the derivative because it is constant, VO is equal to r times the angular velocity of the disk, theta dot. The angular velocity is often written as omega, so we rewrite this equation as VO equals omega times r. The instantaneous acceleration of the center of the disk, AO, is the time rate of change of the velocity. Plugging in theta dot times r for VO and pulling r out of the derivative because it is constant, AO is equal to r times the angular acceleration of the disk, theta double dot. The angular acceleration is often written as alpha, so we rewrite this equation as AO equals alpha times r. Now we will develop equations to describe the motion of the edge of the disk. The origin of the coordinate system is at point C, which is the point of contact before rotation occurs. We will now determine the x-coordinate, x-component of the velocity Vx, and x-component of the acceleration Ax for point C', which is the new position for point C after rotation occurs. The x-coordinate of C' is equal to the distance between points C and A minus the distance between point C' and B. The distance between point C and A is SO. And using trigonometry, the distance between points C' and B is r times sine theta. Therefore, the x-coordinate of C' is SO minus r times sine theta. Plugging in theta times r for SO and pulling out r from each term, we have r times the quantity theta minus sine theta. The x-component of the velocity, Vx, is the time derivative of the x-coordinate. Plug in the equation for x and pull r out of the derivative because it is constant. Now break up the derivative into two terms and take the derivative of each term. We abbreviate d theta dt as theta dot, and using the chain rule, d sine theta dt becomes cosine theta times theta dot. We can pull out r theta dot from each term and substitute VO for r times theta dot. So the x-component of the velocity of C' is the speed of the center of the disk, VO, times the quantity 1 minus cosine theta. The x-component of the acceleration, AX, is equal to the time derivative of Vx. So we plug in the expression for Vx that we just derived, which is VO times the quantity 1 minus cosine theta, and substitute omega times r for VO. Next, we pull r out of the derivative since the radius is constant, and separate the derivative into two parts. In the first term, d omega dt is rewritten as alpha, and the second term is evaluated using the chain rule. We first take the derivative of cosine theta, then we take the derivative of omega. d cosine theta dt is equal to negative sine theta times theta dot, and d omega dt is equal to alpha. Noting that r times alpha is the linear acceleration of point O, AO, we have that AX is equal to AO times the quantity 1 minus cosine theta plus r times omega squared times sine theta. We now will determine the y-coordinate, y-component of the velocity, and y-component of the acceleration for point C'. The y-coordinate of C' is equal to the distance between points C and O minus the distance between points O' and B. The distance between points C and O is the radius r. And using trigonometry, the distance between points O' and B is r times cosine theta. Therefore, the y-coordinate of C' is r minus r times cosine theta. Pulling out r from each term, we now have r times the quantity 1 minus cosine theta. The y-component of the velocity, vy, is the time derivative of the y-coordinate. So plug in the equation for y and pull r out of the derivative because it is constant. Then break up the derivative into two terms and take the derivative of each term. d1 dt is 0 because the derivative of any constant is 0, and using the chain rule, d cosine theta dt becomes negative sine theta times theta dot. Substituting omega for theta dot, we now have r times omega times sine theta. R times omega is VO. So the y-component of the velocity of point C' is the speed of the center of the disk VO times sine theta. The y-component of the acceleration AY is equal to the time derivative of Vy. So we plug in the expression for Vy that we just derived, r omega times sine theta, and pull r out of the derivative because it is constant. We now use the chain rule to evaluate the derivative. We first take the derivative of sine theta, then take the derivative of omega. d sine theta dt is equal to cosine theta times theta dot, and d omega dt is equal to alpha. Next we distribute r to both terms and replace theta dot with omega. Noting that r times alpha is AO, we see that AY is equal to r times omega squared times cosine theta plus AO times sine theta. Here is a summary of the kinematic equations for points on the edge of a disk that rolls without slipping. Let's examine the speed and acceleration of 3 points on the edge of the disk. The first point is at 0 radians, which corresponds to point A. The second point is at pi over 2 radians, which corresponds to point D, and the third point is at 1 pi radians, which corresponds to point E. At point A, Vx and Vy are both 0, meaning the point of contact does not move at that instant. At point D, Vx and Vy are both VO. And at point E, Vx is 2 times VO, while Vy is 0. This means the top of the disk is moving twice as fast as the center of the disk. For the acceleration at point A, the x-component is 0, while the y-component is r times omega squared. For point D, the x-component of the acceleration is AO plus r times omega squared, and the y-component is AO. At point E, the x-component of the acceleration is 2 times AO, and the y-component is negative r times omega squared. If the disk is moving with constant velocity, AO is 0 and the acceleration vector points inward at all points along the edge of the disk. The magnitude of the acceleration is r times omega squared, which is the same acceleration as a particle undergoing centripetal acceleration.